Hello, this is Sareen from Exam Help Lab. Today I'll be solving Chemistry Paper 2 AS Level Structured Questions 9701 Paper 2 read to October-November 2020. Question number 1. Atoms contain the subatomic particles, electrons, protons, and neutrons. Protons and electrons were discovered by observations of their behaviors in electric fields. The diagram shows the behavior of separate beams of electrons and protons in an electric field. Complete the diagram with the relative charge of each of the electrically charged plates. So proton beam deviates towards the right, which means that charge on this plate is going to be negative, and that on the plate here is going to be positive. Part 2. On the diagram, draw a line to show how a separate beam of neutrons from the same source behaves in the same electric field. So neutron beam will pass straight from the source without being deflected because a neutron carries no charge. So a straight line from source without being deflected. Electrons and atoms up to krypton 36 are distributed in sp and d orbitals. State the number of occupied orbitals in an isolated atom of krypton. So krypton 36 has configuration of 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, and 4p6. So there are 4 s subshells present in krypton 36, and each s subshell has got 1 orbital. So in total we have 4 s orbitals. So 4 s orbitals. There are 3p subshells. There is this 2p, there is 3p, and there is 4p. So we have 3p subshells, and each p subshell has 3 orbitals. So in total we have got 9p orbitals. Now there is only one 3D subshell, and that's 3D, and each 3D subshell usually has 5 orbitals, so in total we have got 5D orbitals in krypton 36. Part 2. Complete the diagram to show the number and relative energies of the electrons in an isolated atom of silicon-14. So silicon has configuration of 1s2, 2s2, 2p6, 3s2, and 3p2. Now we have to start filling each orbital of a subshell with meaning first we'll give an electron to all 3 boxes of 2p and then give them their pairs, and then we will proceed to the next level. So 1s2 has already been filled for you. 2s2, we will give them a pair. We will fill each box first with an electron and we'll give them their pairs then. Now 3s2 has a complete orbital. 3p subshell has only got 2 electrons, and those 2 electrons are unpaired. Part 3. The diagram shows a type of orbital. State the number of electrons that exist in all orbitals of this type in an atom of fluorine 9. In fluorine 9 has a configuration of 1s2, 2s2, 2p5. Now fluorine 9 has got just 2p subshell, which has got 5 electrons in 3 of its orbitals. So we have 5 electrons here in the p orbital, which is drawn here. Part 4. The first ionization energies of elements in the first row of the D block are very similar. For all these elements, it is a 4s electron that is lost during the first ionization. Suggest why the first ionization energies of these elements are very similar. Okay, so scandium has a configuration of 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, and 3d1 then, and this continues until copper, though 3d is of a greater energy level and is an inner shell, and 4s is an outermost shell and has a complete orbital. The first electron that is removed in first ionization energy is removed from the 4s subshell, not 3d subshell. They all have got similar ionization energy because the shielding doesn't remain constant even though the number of electrons that are being added are in the same shell. But because the shell which gets an addition of electron is 3d subshell and is an inner shell, so from scandium to titanium atom there is an increase of an electron, and that was added in inner shell, which is 3d subshell, not 4s, because 4s is already filled completely. So as a result, shielding increases when you add electrons in an inner shell. So that extra electron which is added each time you move towards the right, that is added to the 3d subshell. However, nuclear attraction stays similar for outer electrons, for all outer electrons. So we can write that all the way from scandium to copper, shielding increases. And extra electron which is added every time you move towards the right from scandium to copper, that extra electron is added to 3D subshell, which is an inner shell. Also, the nuclear attraction for outermost electrons stays similar. And these are the three reasons why the first ionization energies from scandium to copper, they all are very similar. Part C, hadron, is a general term used to represent the ions state in terms of subatomic particles in the nucleus. What is the same about each of these ions and what is different? So same are all the number of protons, because all these three ions, they have got the same proton number, means same number of protons. And they've got different mass number, which means that they all differ in number of neutrons. Question number 2, the period 3 elements sodium to sulfur all react with oxygen to form oxides. State the trend in acid-base behavior of the oxides of the period 3 elements from sodium to sulfur. So metals, sodium to aluminium, they form basic oxides, and non-metals, silicon to sulfur, they form acidic oxides. So we can write that gets more acidic from sodium to sulfur. Part B, state and explain the trend from sodium to sulfur in the maximum oxidation number of period 3 elements and their oxides. Sodium oxide is Na2O, MgO is magnesium oxide, then aluminium oxide, then silicon dioxide, then phosphorus 5 oxide, and sulfur trioxide. Now you'll notice that oxidation state of period 3 elements will increase across the period. Na over here has an oxidation state of +1, Mg has +2, Al has +3, silicon has +4, phosphorus over here in phosphorus 5 oxide is +5, and S has an oxidation state of +6. And the reason behind that is because of the increasing number of valence electrons from sodium to sulfur. So oxidation number, or oxidation state, oxidation number increases because of increasing valence electrons. Part C, sodium oxide and phosphorus 5 oxide both react with water. Name the product of each reaction. So sodium oxide plus water gives sodium hydroxide. So this is sodium hydroxide. And phosphorus 5 oxide plus water gives you phosphoric acid to H3PO4. So this is phosphoric 5 acid. Part D, explain why phosphorus 5 oxide has a low melting point of approximately 300 degrees Celsius, but magnesium oxide has a high melting point of approximately 2850 degrees Celsius. So phosphorus oxide has got weak intermolecular forces, whereas magnesium oxide has got electrostatic force of attraction between ions of magnesium and oxygen, that is Mg+2 and oxygen 2-, which is, and this kind of electrostatic force of attraction is much stronger than the present intermolecular forces in phosphorus 5 oxide, and thus it requires greater energy for magnesium oxide to break its bonds. So we can write that phosphorus 5 oxide has weak intermolecular forces, whereas magnesium oxide has electrostatic forces, force of attraction, between Mg and oxygen ions, which is stronger and thus requires greater energy. Part E, aluminium oxide reacts separately with both acids and alkalis. Write an equation for the reaction of aluminium oxide with excess aqueous hydrochloric acid. So Al2O3 plus HCl, that gives aluminium chloride plus water. And we will balance our equations. So 6HCl, 2AlCl3, and 3H2O. Write an equation for the reaction of aluminium oxide with excess aqueous sodium hydroxide. Aluminium oxide plus NaOH gives NaAlOH4. Now to balance our number of hydrogen and oxygen atoms, we'll add a water molecule to the left, and we'll have 3 moles of water molecule, 2 moles of NaOH, and 2 moles of the product. Part F, describe the lattice structure of silicon-4 oxide. Your answer should include reference to the arrangement of the silicon and oxygen atoms and the bonds between them. So silicon-4 oxide has a giant molecular structure. That's part of the arrangement of silicon and oxygen atoms. This tetrahedral tells you how silicon and oxygen atoms are connected to each other. Now coming towards the bondings that are present in the structure of silicon-4 oxide, they are made up of covalent bonds. Part G, sodium oxide and silicon-4 oxide react to form sodium silicate. Sodium oxide is obtained from the thermal decomposition of sodium carbonate. Write equations for the following reactions. Sodium oxide plus silicon-4 oxide. This gives us sodium silicate, which is Na2SiO3. That's completely balanced already. The thermal decomposition of sodium carbonate forming sodium oxide and carbon dioxide. So sodium carbonate decomposes to sodium oxide plus carbon dioxide. Question number 3, PCl5. PCl3 and NaCl3 are halides of group 15 elements. PCl5 can be formed from the reaction of phosphorus with chlorine. PCl5 has a melting point of 161 degrees Celsius. Write an equation for the formation of PCl5 from the reaction of phosphorus and chlorine. Phosphorus exists as a molecule P4 plus chlorine gas gives PCl5, 4 moles and 10 moles of chlorine gas. Part 2, state the type of structure and bonding shown by liquid PCl5. So it has got a really low melting point, which means that PCl5 has simple molecular structure and it's between nonmetals, so covalent bonding. Part B, a small amount of PCl5 is added to excess water. The PCl5 reacts vigorously to form a colorless solution. Give one other observation you would make when PCl5 reacts with excess water. So PCl5 is when added to H2O, it gives H3PO4, that is phosphoric acid, as well as HCl, that's hydrochloric acid, and that's the color solution they're talking about. The other observation would be steamy fumes when this reacts vigorously with water. Part 2, write the equation for the reaction of PCl5 with excess water. So PCl5 plus water gives HCl plus phosphoric acid, which is H3PO4, 5 moles of HCl and 4 moles of water molecule. Part 3, estimate the pH of the resulting solution. So because HCl, which is hydrochloric acid, is produced, which is a strong acid, it's going to be around somewhere 1 or 2. So I'll write 1. Part C, PCl3 is used to convert alcohols to chloroalkanes, such as compound T. Part 1, identify a reagent that could be used in reaction 1. So reaction 1 is turning this acid group to primary alcohol, which needs a reducing agent. So I'll write LiAlH4, not NaBH4, because it can only reduce ketone groups back into secondary alcohols, not carboxylic acid group to primary alcohol group. Part 2 exhibits optical isomerism. Explain what is meant by the term optical isomer and circle any atom in T that gives rise to optical isomerism. So it's this carbon atom that exhibits this property, because this carbon atom is attached to 4 different atoms or group of atoms. This has a hydrogen over here, a methyl group, and then there are these 2 different branches. And we can write that an optical isomer is a molecule that has a non-superimposable mirror image. Part 3T is a minor product in the reaction of compound S with excess HCl. Draw the structure of the major product of the reaction of S with excess HCl. So S was the minor product because chlorine, which was added, because chlorine ion that was added to structure S had a choice of attaching to either this carbon atom or this carbon atom. Now coming over to this side, chlorine again had a choice of attaching to either this carbon atom or this carbon atom. If chlorine had attached to this carbon atom, it would have formed a tertiary structure. Again, if the chlorine from on this side had attached to this carbon atom, structure S would have transformed into a tertiary structure. Now, major product will have chlorine attached to such carbon atoms that a much stable product is formed, and that's this tertiary structure. So it's going to be, instead of attaching chlorine on these 2 sides, we are going to attach chlorine to these 2 sides. So chlorine here, and the double bond breaks and chlorine attaches to this carbon atom, which forms a much stable structure. Part D, NCl3 is a yellow liquid that can be used to bleach flour. Predict the shape of the NCl3 molecule and the Cl to N2 Cl bond angle. Now, nitrogen has a lone pair of electron after bonding to 3 chlorine atoms, just like NH3 ammonia molecule. So NCl3 has a pyramidal shape and has a bond angle of 107 degrees. Part 2, NCl3 reacts with water to form HOCl, a weak Bronsted Lowry acid. Explain fully what is meant by the term weak Bronsted Lowry acid. 2 marks, each mark for the term weak and acid. Now, a weak Bronsted Lowry acid is a substance that partially dissociates in a solution and is a proton donor. Part 3, NCl3 decomposes according to the equation shown. A sealed container of volume 250 cm3 contains an unreactive gas at a pressure of 10 to the power pascals. 0.241 grams of NCl3 was injected into the sealed container. The sealed container was heated to make the NCl3 decompose fully into nitrogen and chlorine gases and then cooled to 20 degrees Celsius. Calculate the final total pressure inside the sealed container at 20 degrees Celsius after the NCl3 has fully decomposed into nitrogen and chlorine gases. So starting off with moles of NCl3 that were injected into a sealed container of volume 250 cm3, and they are moles is equals to mass of NCl3 that we'll use divided by the molecular mass of NCl3. So it's going to be 14 plus 3 into 35.5, and that is equals to 0.002 moles. Now 0.002 moles of NCl3 was injected, therefore we are going to have 0.001 mole of nitrogen gas being produced and 0.003 moles of chlorine gas being produced. Now, the increase in pressure is going to be, we are going to be using the formula of PV is equals to nRT. So the increase in pressure is going to be equal to N, the number of moles of the total gases that are being produced, which is nitrogen and chlorine. So 0.001 plus 0.003, that's 0.004 into value R, that's 8.314, into the new temperature, which is going to be 20 degrees Celsius, but we have to take temperature, our new temperature in Kelvin, so that's 293 kelvins, divided by the volume, the total volume of the gas, which is going to be that of the sealed container, and that is 250 centimeter cube. But remember, we have to convert centimeter cube to meter cube, so 250 divided by 100 to the power 3, and we are going to have our increase in pressure as 3.9 into 10 to the power of 4 pascals of pressure. Now they're asking us to calculate the final total pressure, that is going to be the sum of the increase in pressure and the initial pressure. So the final total pressure is equals to 3.9 into 10 to the power 4 plus the initial pressure before NCl3 had decomposed into nitrogen and chlorine gas, and that is 10 to the power 5. This is equals to 1.39 into 10 to the power of 5 pascals. Question before, some reactions of compound G are shown. A part 1 state the type of reaction that occurs in reaction 1. So reaction 1 is turning aldehyde group and primary alcohol group to acid groups. So this is oxidation reaction. Part 2 suggests the reagent and conditions required for reaction 1. So oxidation requires acidified chromate ions, so K2Cr2O7, and the conditions are heat under reflux. Part 3, draw the structure of the organic product H from reaction 2. So the sodium metal reacts only with alcohol group, not with the aldehyde group. So we are going to have aldehyde group as it is, and we will have H being replaced by sodium metal. Part 5, state what you would observe in reaction 3. So reaction 3 is aldehyde group being oxidized to carboxylic acid group with Tollens reagent, which will change its colorless solution to silver precipitate. So colorless solution to silver precipitate. Part 5 gives the type of reaction shown by reaction 4. So this structure has got a carboxylic acid group and a primary alcohol, while this one has got an ester linkage, which means this has undergone esterification. Part B, G and J are structural isomers of each other. Part 1, name the type of structural isomerism shown by G and J. So this is positional isomerism because only position of functional group is varying here in G and J. So positional isomerism. Part 2 suggests one chemical test that can distinguish G from J. Give the results of the test with each compound. G has a primary alcohol group and an aldehyde group, while J has got a secondary alcohol group and an aldehyde group. We can add alkaline aqueous iodine. G will have no change since it hasn't got secondary alcohol or a methyl ketone group or a methyl aldehyde. But J has got a secondary alcohol group, which will give yellow precipitate in presence of alkaline aqueous iodine. So add alkaline aqueous iodine. Alkaline aqueous iodine will give positive result with only methyl ketones, secondary alcohol, and methyl aldehyde. So result with G, it's going to be no change. But with J, which has a secondary alcohol group, yellow precipitate will form, that is triiodomethane. In the reaction schemes below, G and J are converted into organic compound K. Part 3, state the role of NaBH4 in the reactions with G and J. So NaBH4 reacts as a reducing agent. Part 4, identify the organic compound K. Heat and aluminium oxide is usually used in dehydration process, meaning that is the removal of water molecule from the structure. So OH here and OH will get removed and we'll have the double bond present this time. So it's going to be carbon to carbon double bond on the first 2 carbon atoms and on the last 2 carbon atoms. Part C, P and Q have the same molecular formula as G. Complete the table with the expected observations for the reactions of P and Q with the named reagents. Now P with bromine, aqueous bromine, is going to be no change because bromine aqueous mainly reacts with C to C double bond. With Q, again no change. 2,4-dinitrophenylhydrazine with P is going to be no change, because this reagent 2,4-DNPH is for carbonyl compounds only. With Q, it will give orange precipitate. Due to presence of ketone group, which is this one. Now, sodium carbonate with P will give effervescence due to release of carbon dioxide gas. And with Q, there's going to be no change again. Part D, the structure of compound L is shown. R represents a hydrocarbon chain. A student was asked to deduce the full structure of L. The student analyzed L using infrared spectroscopy. The following spectrum was obtained. Identify the bonds responsible for the absorptions marked X and Z. Now, when you try taking these values and match them with your data booklet values, you will know that X is due to carbon to oxygen double bond, is going to be due to carbon to oxygen single bond, that is, and both of them are present in the ester group. Absorption Y shows that L has a C to C double bond present in the R group. The student decided to treat L with hot concentrated acidified potassium manganate. The products of the reactions are shown. Part 2, name M. So M is hexanoic acid. It is a straight chain carbon atom with 6 carbon atoms and a carboxylic acid group. Part 3, use the information in D to deduce the molecular formula of L. Now, these two products after the reaction of L with hot KMnO4 gives 2 carboxylic acid groups. This means that we are going to have C to C double bond and we are going to have hydrogen on each of these 2 carbon atoms. We are going to have CH2 over here and rest of the cyclic structure. And on this carbon atom, we are going to have C5H11. So L has a molecular formula of C12H20O2. Because when this structure undergoes reaction with hot concentrated KMnO4, this will give 2 products, one from this side and the other one from this side. So this carbon will turn into carboxylic acid group. This structure which is attached to this carbon atom will remain as it is. So CH2 and the cyclic structure. While this one on this side will be C5H11. And these are the 2 products which we already are getting. So this confirms that the molecular formula of L is C12H20O2. So that was the end of the paper. Thank you for watching.